Okay, let's do a quick demonstration of the concepts from Structure from Motion. Here's our sample data set. It's from Vulcano Island, north of Sicily, Italy. It's called the Faraglione. And if you look here in this site on open topography, you can see here is Sicily. And if we zoom in, we get to the Aeolian Islands and Vulcano. On this site, which is part of our community data space, you can see where the data are, which in this case are the outputs, but also all the input photographs. So it's a great place to come if you want to practice. Here we're in the software Metashape Metashape Professional, and I've taken the pictures that I collected around the Faraglione, and I flew our Phantom in 2 conical flights over the Faraglione. And so this software does the structure from motion, and the first step is to do the actual structure from motion photo alignment and computation of the scene structure, which is including the pictures and their orientation. So you see the 2 sets of pictures. The blue rectangles are the camera positions, kind of the focal planes, and the little arrows are showing the focal axis. And then underneath there is what we call the sparse clouds. So these points, and if you look down the lower left there, you can see there's 35,612 points. So these are the points with good alignment, good correlation in multiple pictures that SIFT and Structure from Motion identified. Once we have those, then we'll compute the dense cloud, and this is using that multi-view stereo approach. So as you see lower left, there's 22,700,000 pictures in here now. So here, this is a colored point cloud, and we'll hear a lot more about it in the next segment. But each of these is a point with RGB color, so we can see the rocks in this little block, this mountain here, Faraglione. So then the next thing we do, and typically, is we would compute a mesh from these points. And so there it is. There's the wireframe of our mesh. So it's a series of triangles that represent this surface in 3D. And this says there's 1.5 million faces. And so the last typical step then is to compute the texture. So in a sense, we paint onto the mesh the imagery or the colors and pixels that come from the imagery, but they're in the right location as defined by the computations that began with the structure from motion. So this would be a textured mesh, and you could analyze it, maybe look at the dipping layers in this block that may be landslid down from the adjacent volcano. And then the final illustrative point here is if we look a little bit more in detail at these pictures, we had 30 out of 30 align. But if I go to the reference frame here, you can see where the georeferencing comes into play. So longitude, latitude, and altitude are pieces of information that come straight off of the UAS that are pasted into each of the images. Each of these JPEGs has a little header, and it gives us this longitude, latitude, and altitude. And then those provide the initial georeferencing. That's an external georeferencing, and is pretty good for most applications. But usually if we would want something more quantitative and accurate spatially, we would have to add more ground control that was more accurate, because if we look down here at the error, we see there's some angular error in degrees that we're going to tolerate, but also some about a meter of error as reported in the positions calculated by structure from motion, but starting with the positions from the structure from motion. And so we tell it that the accuracy is 10 meters. So in a sense, these positions are in these spheres that are about 10-meter radius. So it's not bad, and it gets us in the right place in the world, but the structure for motion model can have some distortion, sometimes called doming, sitting inside that position with its error. And so we would want to add some higher accuracy ground control if it were important.